So in this video, I'm going to talk about the identical particle or the two-particle system in quantum mechanics. Well, I see a lot of videos online in terms of quantum mechanics about chapter 1, 2, 3, 4 of Griffiths quantum mechanics books, which is the material I'm going to follow here. But I rarely see them cover chapter 5. So I'm just going to try to do that here and help you guys understand chapter 5 better. So let's get started, right? So for a single particle, the wave function, we can write it as phi rt, where r here is the spatial coordinates and t here is time, right? And by the way, if you're watching this video, I assume you sort of have an understanding of chapter 1, 2, 3, 4 of Griffiths quantum mechanics, right, which talk about the normalization, the expectation value and stuff. I assume you have an understanding of that before we begin talking about this. But let's continue, right? So we know that a wave function of a single particle can be written in terms of its spatial coordinates and time. So those are two variables. So what about the state of a two-particle system? Well, the wave function for a two-particle system will be phi r1, r2, and t, right? You simply add one more variable into our function, which is the spatial coordinate of particle 2. And you don't add a time value here because time is the same for particle 1 and 2 in this case, right? So for two-particle system instead of one, we just add one more variable in here. So we know that the time evolution is determined by the Schrodinger equation, which says the following. So IH bar partial phi over partial t is equal to Hamiltonian of phi. And the Hamiltonian here is going to be negative h bar squared over 2m Laplacian plus v, right? Because remember Hamiltonian refers to the total energy. And the total energy in this case consists of the kinetic part and potential part, right? So this Laplacian part stands for the kinetic part of the energy, and then this v here stands for the potential, right? And then the Hamiltonian represents the total energy. So in this case, if we have two particles, well, let me ask you, how do we write our Hamiltonian for two particle systems? Well, since we have two particles, they're gonna have their own kinetic energy for each particles, right? So we can write our Hamiltonian as negative h bar over 2m1. So this is an Laplacian 1 minus h bar over 2m2 Laplacian 2 plus the potential energy. So this is the Hamiltonian for our two-particle system. And this stands for Ke of particle 1. This stands for Ke of particle 2 kinetic energy. This stands for potential, right? It makes a lot of sense. And our potential relies on spatial coordinate of particle 1 and 2 and time. And the statistical interpretation is as the following. Like, this has more to do with normalization, as you have learned in the earlier chapters. But I'm going to explain here. So if we were to normalize this, so if we were to integrate this, what do you think the answer would be? What happens when you normalize a wave function? Well, it's going to be equal to 1. Right? Because remember, when you normalize a wave function, you're basically integrating the whole space, right? And when you're integrating the whole space, the probability of finding that particle in that space is going to be 1, because you started with the assumption that there is such a particle. So in this case, you might be curious then are these two terms of dqr1 and dqr2. So dqr1 stands for the space. So imagine we have particle 1 and particle 2. So this is 1, this is 2. Then dq simply stands for that three-dimensional volume space around the particle, right? And then d cube r2 stands for the space around this, right? And when you integrate the whole space, or when you integrate these two spaces together, it's going to be 1, because that's the probability of finding the particles, and it's always going to be 1. And the explanation for that is from the earlier chapters, and I hope you remember that's actually from chapter 1. Normalization was the first thing that was talked about, and in this case it's the same for two particle system, but you have to consider just two d cube r here for the two particles. So for a time independent potential, so we have phi r1 r2 so t. So this is a time dependent wave function. This can be written as psi r1 r2 e negative I et over h bar, where this right here is a time evolution was it operator? Yeah, operator. And this is a spatial solution. So a way I like to explain this is that we have a wave function that is so dependent of time. So it relies on time, and it also depends on the spatial coordinates of these two particles. So we can break that into two, in which one contains the information about the spatial part of these two particles, and the other one contains the information about how they evolve over time, which is what the second term is, right? So we simply break one wave function that is time independent into a solution which is consists of something to do with time and the spatial coordinate system here. So I'm not sure if that makes any sense, but if you have any question, feel free to leave down below. So our spatial wave function is going to satisfy the Schrodinger equation. So let's write it down first. So negative h bar over 2m1. So let's write down Hamiltonian square, Laplacian square, phi minus h bar over 2m2 Laplacian square to phi plus potential phi is going to be energy phi, right? Because if you really take phi out of the equation here, if you just take phi out, right, what's inside is the kinetic energy for particle 1, kinetic energy for particle 2, and the potential. And if you sum all those up together, what contains inside is basically just E. If you guys can pause the video and try to understand what's going on here, right? So this is just going to be equal to E times phi. So now we have written it down. One difficult task is that solving this equation, finding a solution for it. But there can be two special cases that we can consider. The first case being that the non-interacting particles. So if we have two particles in a system and they do not interact with each other, they're each subject to their own external force. So you can imagine them to be independent of each other. In that case, the total potential energy is sum of the two. So the potential part of the energy. So we usually write it as V R1 R2, right? Now it can be broken down as V1 R1 plus V2 R2. Because if these two were to be independent of each other, then we can write the total potential energy as the summation. So physically, this might mean each particle only feel its own potential. So the net potential in the system will be a summation of their own potential, because we're assuming no interaction between them. So now, because the potential is separate, we can have a product form of the total wave function. So this part might be a little confusing if you're just reading off the textbook, but I'm going to try my best to explain here, right? So you can see the textbook writes this form. So you might see, okay, where is this coming from? Like, what is this about? Well, if you recall back to our original case, so when we have kinetic energy particle 1, and we have kinetic energy particle 2, and potential has both particle 1 and particle involved in them, right? So now if I tell you our assumption, which is that they're non-interacting and that their potential are independent of each other, then you can write this as kinetic energy 1, kinetic energy 2, V1, and V2, right? Because in the case we discussed before, we didn't assume them to be independent. So although their kinetic energy is different for their own particle, but the potential part is will bind them together. But now if I start with the assumption that they don't interact with each other and that the potential is independent of each other, we can take these two out, right? They're no longer binded as in the case before. And if they're no longer binded, then we can write our wave function as a product of KE1 and V1, KE2 and V2, right? So now since the potential are no longer bind together, we can group KE1 with V1, KE2 with V2, right? And that is what's happening in our case here. If you're looking at the case we have here, right? We've broken down our original wave function into two parts, and phi A is particle 1, phi B is particle 2 here, and their own term includes their own kinetic and potential, since the potential is no longer binded and they're independent of each other. So I'm just going to repeat that. So now I'm done with explaining all of this. Oh, I accidentally wiped that. So you guys might pause the video, go back and listen to this part a little bit more, because it might sound kind of confusing. But again, if you guys have questions, just keep asking me. So we're going to continue with our derivation. So if we substitute this equation into this equation here, then what we get is, so I hope you guys already written this part down, because I'm about to zoom in and write the whole expression. So you might be able to not see it, but this should be equal to negative h squared 2m 1 Laplacian, right? We're replacing our phi with this, so we're just gonna write phi A, R1, phi B, R2. And the second part is going to be the Laplacian for particle 2 of phi A, R1, phi B, R2. And then we have plus our potential. So plus our potential. In this case, our potential, right, is V1 R1 plus V2 R2. So V1 R1 plus V2 R2. This multiplied by our wave function. You see, it's not fitting anymore because I'm writing them too big. But this should be easy to follow and for you guys to write down too. And this is going to be equal to E phi. So in this case, E phi is going to be E phi A R1 phi B R2. So what we have done here is simply replace all our phi here with our new expression of phi in terms of phi A and B, and we have replaced our potential and original this potential term right here with what we have here. So this is the whole expression we have. And there is a very important observation to be made here, is that look at our Laplacian, right? So for our equation 1, so not equation 1, but this part of the equation, when you have Laplacian 1, when you apply Laplacian 1 to this whole phi here, then you can realize that phi b r2 can be taken out, right? Because our Laplacian operator here for this part of the equation is specifically designed for particle A, so or 1. So R1 is going to remain here, while our phi b R2 is going to be taken out because that was not part of our original Laplacian for particle 1. So that is a very important observation that you can make. So and what you can do with the potential part is that you can group the V1 R1 with phi A R1 and V2 R2 with phi B R2. So the expression, by using this assumption of taking phi b out of it, well, it was the same thing going on here, right? We have Laplacian 2, so phi a can be taken out as a constant in this case because it's just a constant factor, right? The Laplacian in this case is a the phi b in this case is a factor with respect to phi R2, and it doesn't act on R1. So in this case, we can take these treat these as constant and take them out. So once we take them out, then the expression becomes, well, let's write them again. So for the first one, we take phi b out. So this is gonna be, I'm gonna try to write more neat this time, so I don't run out of space again. But this is what you're gonna have, right? And the potential part, remember we grouped the potential, the V1 R1 with our phi A R1, right? So particle 1 with particle 1, particle 2 with particle B, kinetic 1 with potential 1, and kinetic 2 with potential 2, plus V1 R1 phi R1. I can recommend you guys maybe want to pause the video and continue to write this and then compare with what I write down and see if you guys are correct. So phi A R1, because for the second one you take the phi A out, I already explained that, negative h bar over 2m2 Laplacian 2 square phi b R2 plus the potential, which is V2 R2 phi b R2 is going to be equal to our energy, phi A R1 and phi b R2. And fortunately we didn't run out of space this time, but we have obtained this equation. So we can do a separation of variable here. So if I were to ask you, if I want to isolate E here, so if we want to isolate this E energy, what do we do to our situation? Well, we divide this whole equation by phi A R1 and phi B R2, right? So you can pause the video and do this calculation yourself, but when you divide this whole equation here, divide by phi A R1 phi B R2, or in other words, this whole equation over this, you obtain the following expression, right? Phi A R1 for the first term, right? Because remember, you have phi B R2 here, and if you were to divide, then the phi B R2 will cancel out here. But you still have to divide by phi A R1. So that's just basic algebra at this point. You guys should be able to understand this part. So I'm just writing down the equation again. 1 plus V1 R1 phi A R1, feel free to skip ahead if because this writing is sort of, I wouldn't call it unnecessary, but it's sort of the part where everybody just understood it, what's going on, but you still gotta write it down in the end of the day. R2 phi B. R2 is going to be equal to E, right? Because we have isolated E by dividing the left equation by phi A R1 and phi B R2. So know what we have here is that what this stands for is the energy for particle 1. So this we can call it, well, EA. I think that's correct. Let me just recheck everything that we have here. So note that the first part is energy A, which is energy of particle A, and then the second part is energy particle B, and there's summation. So E is what we have on the right side, so E must be equal to EA plus EB, right? Because our total energy must consist of the energy of particle 1 and particle 2. And in this case, EA, yep, this seems to be correct. So once we have this assumption, the next part is, let me check the textbook. Yeah, I think I just remember now that, so if we know this first part is about energy, let's call it energy A here, and this part is about energy B here, right? And if they were to make up E, so if this whole part, so if negative phi R1 if this were to be equal to EA, right? Then if we move this to the other side by multiplying EA by phi R1, then we can obtain, so we can now know that the total energy for this part is just going to be EA phi R1. And the same goes for EB, phi B R2. And we know that E is equal to EA plus EB. So now we have talked about the spatial part of the two-particle system. What do I mean by that is that if you look at all the calculation or all the plug-in we did, you realize that the variable time is missing from our case, right? So we have done talking about R1 and R2, which is what all of this is about. Now we have to talk about the time-dependent part of the wave function. And for particle A, so phi A R1T. So for particle A, the solution is going to be phi A R1 times the time evolution operator, which I have mentioned earlier. And phi B follows the same logic. Oh, phi B R2 times E. Right, and you might ask, okay, what is this term? Where is this coming from? So I have already explained it in the earlier part when I did this, but if you really unsure about how this part came about, you can review the previous chapter, which talk about the solution, the general solution to a wave function, and this part is the time evolution operator part, and this part is the spatial part. And this was talked about in chapter 3, like the general solution of Schrödinger's equation or something like that. But we should move on with our case and realize that we have two separate solution for our two particles. So the total wave function, which is the two particle system here, where we consider R1, R2, T. Remember, this is equal to phi A R1 times phi B R2. So it's equal to these two times each other, which is going to be phi A R1 EATH. Oh, here I made a mistake of filling out EA, but this should be in fact EB times phi B R2 e to the power of negative IEB T over H bar. And this whole thing is going to be phi A R1, phi B R2, and then our time evolution operator. But in this case, the energy is going to be EA plus EB T over H bar. So, and this is going to be equal to phi R1, R2, T, right? This is what we have here. So what does this really tell us? Well, what you can do is actually further simplify what we have here. So this whole equation. So remember how earlier in the part I talked about how, like in this part I talked about that phi R1, R2, T can be broken down into a spatial solution and a time evolution operator, which is what we have here. Well, we can do the exact same thing for our case here, right? So now we were to revert what we did here. So instead of breaking this into this whole thing right here, we want to revert. So when we revert, we realize that, well, we have time evolution operator for A, we have time evolution operator for B. So revert would simply be putting a time variable into our spatial solution. So phi R1, R2, T is going to be phi A R1 T times phi B R2 T. Right, this is what we have here. Because so phi R1, R2 T is consists of these two parts, which is corresponding to A and B. And for the A part, you have the spatial solution and the time operator, the time evolution operator. So this just turned into phi A, R1, and T, right? Similar, it's like a revert of what we did here, of taking this time variable out into a time evolution operator, but we're simply reverting that, which is what we're doing back right now, right? We're turning this whole thing back into this for both of these equations. So you're going to obtain this formula for both. Now this has a pretty important implication, because recall, in quantum mechanics, any linear combination of a solution to the Schrödinger equation will also satisfy that Schrödinger equation. So what do we mean by that? And what implication does that have? Well, what do we mean by the linear combination? Like I tend to think of an example of if you have y and x is a solution to y, to our equation here, right? So any linear combination, so x itself is a solution, x plus 10x is a solution, x plus 10 0 0 0 x is a solution, or the other way around. So that's what we meant by linear combination. So if x is a solution to y, then x itself is a solution, x plus the multiple of itself is another solution. So that's what we mean in this case. Now you might ask, okay, so what does that imply? Well, that implies if this is a solution to our equation, then any alpha times phi 1, R1, R2, T plus beta phi 2, R1, R2, T is also a solution, valid solution for our case, right? Because if these two solutions, if our phi A and phi 2 are both valid solutions to our Schrodinger equation, then any linear combination, which is what I have right down here, is also a valid solution for our case. So in the textbook, it written down such an example, which is consider the case of phi of the following: R1, R2 is equal to 3/5 phi A, R1T, phi B, R2T plus 4/5 phi C, R1T, psi D. R2T is, in this case, the particle 1 depends on the state of particle 2. So if you measure the energy of particle A, so what are you going to get when you measure the energy of particle A? Well, you get EA, right? And if we know the total energy, so if we know the total energy, and we have measured EA, so EA now is a fixed value, the wave function collapses, we know what EA is. Then by simple algebra, because we know EA plus EB must be equal to E, then we can figure out EB. And this is very interesting because this is actually what we call quantum entanglement, which you might have heard a few times, or a lot of times if you watch a lot of those physics videos. We say these two particles are entangled, right? Because there is some sort of probability and uncertainty to the energy A and B, right? Like it's just like the position or the momentum, like there's some sort of uncertainty or probabilistic aspect to the energy A and B, right? But what happens when they're entangled is that if you measure energy A, you can always know energy B. You guys might have heard in the physics video where they might have talked about if you found the spin of one and then you know the spin of the other one, right? So it's the same case here. If these two particles are entangled, if you know the energy of one, you know the energy of the other, because the net energy must be the same. And since the energy for each are sort of probabilistic, right, then that's kind of interesting because if you place a particle on the moon, so particle A is on the moon, particle B is on the Earth, and when you measure particle A, so like particle A's energy, so EA has some sort of uncertainty to it, like is not a defined value each time. Like the exact value is determined when you observe or when you measure the energy, right? So when it's determined at the energy, somehow the particle B on Earth, which is 380,000 kilometers away, instantly you know the energy of that, knows the energy of that to be something else. So if if E is equal to 2 or E is equal to 3, right? If you measure EA to be 1, then somehow EB must be 2. Or EB has some way of knowing that you have measured 1. Like this is not a very good analogy that I just made here, because I realized that if E is equal to 3, and we know this is 1, like I sort of we know EA is 1 and EB is 2. I sort of assume that you already know, or the energy for EA is already fixed at 1, and the energy for EB is fixed at 2. But that's not the real case here, because remember, in quantum mechanics, it's probabilistic, right? So in reality, this could be like 0.5, or this could be 1.5, right? And you realize that since the net energy stays the same, so EB must sort of change different value according to 1, right? Like, how could EB instantly know what EA was measured to be when it's so far away? Like, this is the exact question that Einstein thought about, because the exact value, so 3 is equal to some A plus B, where A and B are both probabilistic. And when you determine A, instantly, somehow particle B knows its own value. Like, that shouldn't be the case. Like, there's, like, look at the different cases I made here, right? Like, the first term A could be 0.1, could be 1.5, could be 1, right? So it's sort of probabilistic. It's not a determined fixed value at a certain point. And when you actually make the measurement, the superposition or the wave function collapse, and it falls into one of these three, either be 0.5, 1, or 1.5. And when you have two particles very, very far away from each other, like the moon and Earth's example I talked about, somehow, instantly, when you measure 1, particle B knows the outcome of A, and that speed is faster than the speed of light. Like, that's what Einstein is confused about. And that is the case here, which back to what we were just talking about, is what we call entangled state. Because remember, this is also a valid solution to our Schrodinger equation, right? Because this expression right here is just a linear combination of what we have here. So these two are both valid solution to our two-particle system Schrodinger equation, or a wave function here. And in this case, right, you can, and these two are called entangled. And an entangled state is one that cannot be written as a product of single particle states, which is what we have here. Like, these two are written as a single product of two particle states, right? And the entangled one is where it cannot be written, because you see in this case that the textbook brought up, they're entangled and is sort of like addition or some summation of these two, right? It's like a linear combination. So to sum that up, so we find this to be the solution. And from the quantum mechanics principle, we know if this is the solution, then the linear combination of this solution must also be a solution to a Schrodinger equation. So from that conclusion of linear combination must also be the solution, we come up with this example that textbooks gave us. And it is entangled when it's in this case of, like, the state of particle 1 depends on the state of particle 2, or vice versa. We call them so-called entangled in this case. And that's all I have to talk about for 5.1.1. So the next video, I'm gonna try to talk about bosons and fermions. But if you guys have any question about what I have just talked about, feel free to leave a comment below. And I'm sorry for if there are cases or if there are instances where my talking was sort of confusing, because I have this learning disability in which when I talk, I often sometimes forget what I was talking about. So that's just my apology. If you have any questions, feel free to comment on, and I will look at each one of them and try my best to answer them. And I hope this video helped you understand anything about two particles or identical particles. And thank you guys for listening.